Alrighty, this is example number 10 on page 270. This is an example of curve sketching, and we are specifically looking at a rational function. So when you look at the directions in the textbook, they tell you to follow their guidelines. I want you to follow my guidelines, which will mirror what we did in our notes during class. So first thing we're going to do is we're going to find our domain, x-intercept, y-intercept, and our asymptotes. Then we'll look for first derivative information and second derivative information. All right, to test your domain, we're going to start by setting our denominator equal to 0. And it's x minus 1 squared, but really that's the same factor twice. So I'm going to set x minus 1 equal to 0, which tells us that at x equals 1, we have a break in our graph. So my domain would be everywhere but 1, so negative infinity to 1, and 1 out to infinity. For our x-intercepts, we are going to substitute 0 in for y. So 0 equals x over x minus 1 quantity squared. We know that when a fraction equals 0, that only happens when the numerator is 0. So you can just set the numerator equal to 0, which gives you 0, 0. Or you can, if you forgot that, just drop a 1 underneath there and you can cross multiply. For our y-intercept, we substitute a 0 in for x. So we're going to have y equals 0 over 0 minus 1 squared, which is 0 over 1, which is 0. So that would be the same exact point, the same x-intercept and y-intercept since it's at the origin. For your horizontal asymptote, we're comparing the degree in the numerator and denominator. So you don't have to actually expand it out. Sometimes that power is too high to do that, but you do have to envision what this would be if you expanded it out. That would be an x squared. Of course, if you continue, that would be minus 2x plus 1. And my denominator has a greater degree, which means my horizontal asymptote is at y equals 0. If your numerator was a greater degree, there isn't a horizontal asymptote. If they are the same degree, you grab the quotient of their coefficients. And then for my vertical asymptote, I'm looking for where my denominator is equal to 0, and I want to make sure it's not a removable discontinuity, a hole. And I already know that my denominator was 0 at x equals 1. Nothing is canceling on top and bottom, so that 1 is not a hole. So that means it is, by default, a vertical asymptote. All right, next step, I'm going to be looking for first derivative information. So I'm going to take the first derivative of y. So this is going to be y prime. I'm going to use my quotient rule, low d high minus high d low over low squared. So low is going to be x minus 1 squared, d high, derivative of x is 1, minus high is x, derivative of the bottom is 2 times the quantity x minus 1, power drops down to a 1, times the derivative of x minus 1, which is 1. That's your chain rule right there. And then all over your denominator squared. Okay, so I know I need to set this equal to 0, so you can either clean this up first or you can factor. I like to clean it up a little bit. So we have x minus 1 squared. On this side, I'm going to combine my 2x. X times 2 times 1 is 2x times x minus 1. And while these powers aren't very high, you could just distribute and clean that up if you want, but I'm going to go ahead and factor. So I'm factoring out what they both have in common, which is an x minus 1. And when I factor that out, I'm dividing. So x minus 1 squared divided by x minus 1 leaves me with x minus 1. And when I divide this by x minus 1, I'm left with just minus 2x. All over x minus 1 to the 4th power. And I am seeing that my x minus 1, now that this is in a factored form, a multiplied form, that x minus 1 on top will cancel with one of those on the bottom and leave me with an x minus 1 cubed. And I'm going to go ahead and clean up that numerator. And I know I have to set this equal to 0 at some point. X minus 1 minus 2x, so x minus 2x is negative x minus 1 all over x minus 1 to the 3rd power. We're going to set my numerator and my denominator equal to 0. Why do we do that? We're looking for where f prime equals 0, and we're looking for where f prime doesn't exist. Those are going to represent our critical values. So our function here doesn't equal 0. It equals 0 when my numerator is 0. So I'm going to set my numerator equal to 0. My first derivative doesn't exist when the denominator is equal to 0. So we have negative x equals 1, x equals negative 1, and over here, x equals 1. So we are ready to plot this on a number line. We have negative 1 and 1. I'm going to substitute those numbers into my first derivative. So a number less than negative 1 would be negative 2. So negative 2 would be positive 2 minus 1 is positive. Negative 2 minus 1 is negative, cubed is a negative. So that quotient would be negative. Let's substitute 0 in. 0 minus 1 is negative. 0 minus 1 is negative cubed is a negative. So that quotient would be positive. Let's substitute 2 in. Negative 2 minus 1 is negative. 2 minus 1 cubed is positive, which is negative. Okay, so let's identify our increasing interval, our decreasing interval, and then any local mins and any local maxes that we might have. So this is increasing when my first derivative is positive. So from negative 1 to 1. It is decreasing from negative infinity to negative 1 and from 1 out to infinity. This function at negative 1 is decreasing and then increasing, so that is going to be a minimum. And at 1, it's increasing, decreasing, that is going to be a max. So my minimum is at negative 1. I'll plug that in just a second. My maximum is at 1. All right, we're going to substitute these values back into my original function way up here. So I'm substituting into y. So f of negative 1 would be negative 1 over negative 1 minus 1 squared. So that's negative 1 over negative 2 squared, which is 4, so negative 1/4. For my maximum, I'm going to substitute a 1 in. So 1 over 1 minus 1 squared. Oh yeah, look, I'm getting an undefined number. Why is that happening? What's happening at 1? Remember, 1 came from when the derivative doesn't exist. Why does the derivative not exist? Remember, that's where our vertical asymptote was. That's also where we had a break in our domain. So if I go back to my number line, this was actually a vertical asymptote, not in fact a maximum like it looked like. So I'm going to cross off local max. We do not have a local max. All right, now we're ready for the second derivative. So I'm going to take my first derivative, scoot this down here. I'm going to take my first derivative and find its derivative. So that would give me my second derivative. And we are using our quotient rule again. So low, d high, derivative of the top is negative 1, minus high, d low. So the 3 comes to the front. X minus 1 carries down, so you can drop down the power to a 2 times the derivative of the inside, which is 1. And that is all over my denominator squared. Okay, so we're going to factor this thing. I'm going to clean it up first also, I think. So we have a negative in the front times the quantity x minus 1 cubed. Over here, I'm just going to combine the negative 1, the 3, and the 1 to give me a negative 3 times negative x minus 1 times x minus 1 quantity squared, all over x minus 1 to the 6th. You might be tempted to expand this out and add like terms. I wouldn't even go there. Once your powers are higher than squared, it's a lot of work. So we are going to work this faster by factoring. So what can I factor out of these two terms? They both have an x minus 1. And I'm going to grab the smallest power, which would be my squared. So what am I left with here? That negative comes down. When I factor out, I'm going to divide. So I'm subtracting my powers. 3 minus 2 is a power of 1. That minus 3 carries down. My negative x minus 1 carries down. And the x minus 1 squared divides by itself, so that's gone. On the bottom, we have x minus 1 to the 6th power. So what do we have to do now? We're going to clean up that top portion. And I'm also seeing that we have an x minus 1 on the top and the bottom. So those two will cancel with 2 of these and drop that down to a power of 4. And I'm going to clean up that numerator. So we have negative x plus 1 plus 3x plus 3 all over x minus 1 to the 4th power. So that would give me positive 2x plus 4 over x minus 1 to the 4th power. And if you wanted, you could go one more step where I factor a 2 out. And I have 2 times x plus 2 over x minus 1 to the 4th power. Okay, we're going to set our numerator and our denominator equal to 0. So if I set the 2 equal to 0, I get nothing. So I'm going to set my x plus 2 equal to 0. Basically, I'm setting every single factor equal to 0. So I have negative 2 as a critical value, and I'm going to set x minus 1 equal to 0, so I have 1 as a critical value. So we're going to plot negative 2 and 1 on a number line, and we're going to test those values into my second derivative. So let's substitute negative 3 in. So negative 3 plus 2 is negative. Negative 3 minus 1, hey, anything raised to the fourth power is always going to be positive, so that is not going to change. So a negative over a positive is a negative. Let's substitute 0 in. 0 plus 2 is positive. The denominator is going to be positive. So positive over positive is a positive. Let's substitute 2 in. 2 plus 2 is positive. 2 minus 1 is positive. So that is also a positive. You'll recall at 1, that was a vertical asymptote, by the way. All right, so we're going to identify our concave up and our concave down interval. This is concave up everywhere that this second derivative is positive, so that would be from negative 2 to 1, and also 1 to infinity. We do list this as two separate intervals because at 1, our derivative either was equal to 0 or didn't exist. So it was definitely not concave up at 1. And it is concave down from negative infinity out to negative 2. We have a point of inflection, or an inflection point, at any concavity sign change, and we have a sign change at negative 2. So I do need to substitute negative 2 in back into my original function. So negative 2 over negative 2 minus 1 squared. So negative 3 squared would give me negative 2/9. Okay, we are ready to sketch this thing. So when we're sketching, we know we're going to be sketching these three important features. And I like to point out which ones are actual points. So I know the point of inflection is an actual point. Let's go back to my first derivative information. I know I'm going to be plotting all of this information on there, and the local min is an actual point. And then going back to the beginning, I'm going to be plotting my x-intercept, y-intercepts, and my asymptotes. And these are actual points, and the asymptotes we know with absolute certainty as well. Okay, so let's go ahead and start our xy coordinate plane here. When you're choosing what x values you need on here, you look at all your points. So I have negative 2, I have negative 1, I have my intercepts at 0, and then my asymptotes. But you can also look at your number lines. So my first derivative number line and my second derivative number line. Negative 1, 1, negative 2, 1. I'm going to have to plot all of those on this graph. So I know I need negative 1, I need negative 2, I need 1. I'll just draw a 2 on there. Okay, and in terms of our y values, negative 2/9, negative 1/4, those are the only ones we're going to need. Negative 1/4, remember, is negative 0.25. Negative 2/9 is negative 0.2 repeating. So negative 0.25 is lower. So I'm going to put my negative 2/9 here, my negative 1/4 here. All right, so let's get some things on paper here. Let's get our actual points that we know. So going back to the very beginning, we have our x-intercept and our y-intercept at 0 and 0. We have our horizontal asymptote at y equals 0. We have our vertical asymptote at x equals 1. We have a point of inflection at negative 2, negative 2/9. I'm going to label that IP or POI. And then we had a local min at negative 1, negative 1/4. Now, typically, our local mins look like this. So I'm just going to sketch them with a pencil for right now. I'm also going to put my increasing, decreasing intervals on there and my concavity. So for my increasing, decreasing intervals, it was increasing from negative 1 to 1. So I'm going to drop that in here. So negative 1 to 1. I am increasing. It is decreasing from negative infinity to negative 1, and then from 1 out to infinity. So in just looking at our curve, this graph is decreasing. Well, it has to come from my asymptote, right? So it's going to come from the asymptote. It's decreasing. It's going to go through this point, negative 2. It's going to keep decreasing. And then it hits this little minimum down here, and then it switches to increasing, 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 increasing. Then it's going to head up towards infinity. And then this function has to be decreasing after that. So it has to come from up top. If it came from down the bottom, it would be increasing. And I know it has to flatten out to approach that horizontal asymptote. So I already have a really good idea of what this is going to look like. Let's look at our concavity though. So this is concave up from -2 to 1. So this whole interval here, it is concave up. It is concave up from 1 to infinity also. And then it is concave down all the way over here. So -infinity to -2. All right, so when I'm sketching this thing, I know I'm coming from the asymptote, and it is concave down. So it's going to look something like this, and it's decreasing. And then it switches to concave up. It's still decreasing, but it's going to go through this minimum. And then it switches to increasing, and it is concave up, concave up. It's going to pass through that 0, concave up, and it approaches that asymptote up there. And then on this side, it is decreasing, and it is concave up. So it is going to look something like this, and it has to approach that horizontal asymptote out here. Okay, so thank you so much for listening. I wish you all the best. That was example number 10.